Thanks for having me. Like I said, I'm coming in virtually from Greece right now, visiting Stavros Papadakis and Vaso Petrotou together with Adiprasito. So it's joint work of all of us. Hence their names are right there. Oops. There we go. All right. Our protagonist for the day is going to be a lattice polytope. So by that, I really just mean convex hull of a finite set of integer points or integer coordinate points in the lattice. And then the classic thing is to do Ehrhart theory on it, where, fun fact, Ehrhart was a high school teacher in France who happened to show in his spare time that if you take this here, just this function, so we take the polytope and dilate it by an integer factor of I, if you count the number of lattice points that this contains and take this as a function from n to n, so given a number I, how many lattice points does the I dilate of that polytope contain? That is a polynomial called the Ehrhart polynomial. He proved this and sort of started the whole field. And we do it still. And something nice that you can do with it is turn it into a generating function. Only a couple of people will view that as pain, but that's fine. I view it as pain too. We'll get out of the generating function quite quickly. And it turns out to be a rational function, and you get a polynomial up here. Another fun fact is if you take the Ehrhart polynomial, the leading coefficient is going to be the volume of the polytope. You can plug in negative numbers and get the number of lattice points of the interior. There's a bunch of beautiful things that you can do hands-on with Ehrhart theory. But we're going to view it a little bit differently as a semigroup, first of all. So we take our polytope and embed it in one dimension higher at height 1, and just take the cone over it. So we have our polytope here, take the cone over that, and now what is counting the number of lattice points in the ith dilate is the same as just saying, okay, I take this cone, I intersect it with the lattice again, and then I count the number of points at sort of height I. I slice it, count the points. Okay. Now, just this cone intersected with the lattice is going to act as a semigroup just by vector addition. And we say that our polytope has the integer decomposition property, or by abuse of grammar, we say that it is IDP if this semigroup is generated exactly by the points here in the lattice polytope. Now, every polytope considered in this talk is going to be IDP. So this group is always going to be generated at height 1. Okay, if we want to do a bit of algebraic combinatorics, a group is not going to be enough. We want to take an algebra over that group. So pick your favorite field and put the semigroup as the variables, or as the exponents. Start the sentence from the beginning. Take an x to the m for every m in the semigroup algebra. So our lattice points are going to be our exponent and the exponents of our variables. Okay, and just as a sanity check, this is the same as if I had just said, take those that are in the polytope at height 1 and generate the group over that, then take the semigroup algebra. This is Combinatorial, so we can work with it well. It has codimension d+1. And it's graded by the last coordinate, right? The coordinate, the height of whatever dilated the polytope we have. So since it's Combinatorial, we can do nice things with it. We can pick a linear system of parameters in degree 1 and take the ideal spanned by those and mod it out. And then we get an Artinian reduction. Now, I hope I put this everywhere in the slides. I have a little theta here just to remind ourselves that this Artinian reduction really does depend on the choice of thetas. They are highly important. Now, we know that whatever linear system of parameters we choose, we do get that the dimension, just as a vector space, of this kth graded piece of the Artinian reduction is going to be exactly the h star k, the ones that we had right here. And these are the numbers that we're interested in. Okay. So we've encoded them as the dimension of graded pieces of an associated Artinian algebra. And if my tongue slips, I might call it a chow ring every now and then for reasons. Okay, now the other thing that we want to assume in this talk, technically the results go broader than that, but the nicest case and sort of the originally conjectured case is for reflexive polytopes. Now I put down a whole bunch of different versions to define what makes a polytope reflexive. Pick your favorite one. Maybe if you've never seen any of this before, take this one, just because it's maybe the easiest to check and because we use it. If you want to see the algebraic reason behind this, which is most of the game of what we do, is trying to figure out, okay, we have some combinatorial shadow, where does it come from algebraically? Then see that it really comes from this part here. So we have a perfect pairing for any reflexive polytope from the kth graded piece with the d minus kth graded piece. So exactly on the other side. So for every element here, we can find an element here such that when we multiply them together through the group, through the ring, then the result is going to be non-trivial. We always find some, for every element in degree k, we can find an element in degree d minus k to pair it with non-trivially. Now I put this little degree thing here, that is this isomorphism, which is technically quite important. We're not going to go into it too deeply, but it does matter. Okay, and then whichever one of the other ones you like. Okay, this you might like if you're an algebraist. These you might like if you like polytopes in general, and this is sort of the middle ground between the two. Pick your favorite. Okay, from now on, every polytope is not only IDP but also reflexive. For visuals, a picture that I shamelessly stole from a paper of Hazard Mernikov, a beautiful paper, an illustration of all of the different two-dimensional reflexive polytopes up to equivalence. Okay, here's the main conjecture. This is a special case of a more general conjecture of Stanley's. Now, the very general conjecture of Stanley's wasn't quite true in all cases. It's been refined. People changed the conjectures every now and then. This version is due to Hibi and Ohsugi, saying that, okay, if our polytope is reflexive and IDP, then this H star polynomial, the coefficients are going to form a unimodal sequence. So it's going to rise up to the middle and then go back down. Now, not what I said a slide ago, well, 2 slides ago. Here, we know that we have a symmetry already. We know that it's a palindrome, but we would like more than that. We would like it to even be unimodal. Now, history. If our polytope is not only IDP and reflexive, but also admits a unimodular triangulation, a regular one, then this was already known, this was already proven by Athanasiadis. Okay, I'm bad with Greek names. By these 3 people, based on Stanley's G-theorem result. Effectively, what it boils down to is that if you have a unimodular triangulation, the H vector of that unimodular triangulation is going to equal the H star vector of your polytope. And for a reflexive polytope, what you can do is you have the H star vector of the polytope exactly equal to the H star vector of sort of the boundary, if you view it as a as a complex of lattice polytopes. And so what you do here is you triangulate the thing, but really what you have is you have a star with one vertex in the middle, one point in the middle, and you have an H vector of this star that is the same as the H vector of this boundary. Now the boundary of is just a polytope. So this is going to be the H vector of a polytope that we can apply Stanley's G theorem to. You can generalize this by the same argument of the unimodular triangulations without the regularity if you instead use Karim's G theorem from simplicial spheres. So you're using heavier machinery, but the argument remains the same. Questions so far? Including or including on slide 1, I missed something important. That is also perfectly fine as a question. Okay, now, how do we prove any of this? Right, you might have seen a lot for these unimodality results that we have a kind of Chow ring that we associate, and then we prove a Lefschetz theorem on it. / if you go more the route of Juni-Ha, you often prove Hodge-Riemann relations on them. And in the classical case, these come as a package together, as the Kähler package. You prove them sort of one after the other, back and forth by induction, going up the dimensions. If you want to push the theory a little further, though, you end up being able to prove one without the other in both directions for more specific cases. So you have a bunch of theorems in the Hodge-Riemann sort of crowd where you don't have the Lefschetz theorem at the same time. And for us, we're doing the Lefschetz theorem without ever doing the Hodge-Riemann relations. But in order to do that, we need something specific on the thetas, right? I said that this LSOP is very important, and it's important in the following way. Main theorem, the Lefschetz theorem. So say we have our lattice polytope, we have that it is IDP, we have that it is reflexive, and then we choose our linear system of parameters, our elements in degree 1, generically, then mod them out, the ideal span, but then we mod it out. Then it has the Lefschetz property, the result. So then we can find a linear element in our ring such that we can multiply it through to get an isomorphism. Now, first of all, say that you have a Lefschetz theorem for one specific Lefschetz element. So this little L we often call a Lefschetz element. Say you've been lucky and found one. This is, or clever and found one, hopefully. This is the standard path. This is the way you would do it for a polytope. You have a good way of finding it. You have an ample cone, you have nice convexity to use. Then given one, any generic choice would do. Why? Well, what you're really proving is these are vector spaces, nothing more. We're really just doing linear algebra at the end of it. These are vector spaces, so you have a map between vector spaces. And all you're proving is that things are injective or surjective, maximal rank, matrix questions. So you're really just asking something about determinants going to 0. Okay, so if it works for one specific element, it's going to generically not go to 0. So you can choose it generically. It's going to be a Zariski open condition on these coefficients that this one carries, right? This is an element, this is just the sum of variables, right? The sum of the things that span this or that generate this. Okay. So say we have this, how do we get the conjecture? Okay, we have an isomorphism from the kth piece to the d minus kth piece, right, by multiplication. So that just means we go from the kth piece to the k+1, k+2, and so on and so forth, piece by multiplication. We keep going up higher. And okay, I have an isomorphism together that is just a concatenation of a bunch of functions. The first one is going to have to be an injection. The second one is going to have to be an injection here, because I can now take off a piece from the left. It can take off a function from the left. I can take off a function from the right, one of the multiplications. We still get it. Then we repeat it. We go from k to d minus k. This is an isomorphism. In particular, it's an injection. In particular, the first map in this composition from k to k+1 is going to be an injection. Okay, this is an injection between vector spaces. So we have an inequality between their dimensions. We know that hk is the dimension of this vector space. This is smaller or equal to this one. Okay, we have it. This is all we're trying to prove. We're trying to prove this for every k in the first half. The upper half is either analogous or by symmetry, right? We know that we have a palindrome anyways. So we can just flip the information and we're fine. Everybody okay with going from Lefschetz theorem to the conjecture? All right. Now, how do we ever prove any of this? This is the difficult part, right? Because we've lost the convexity. And so the standard way would have been to be clever at finding this Lefschetz element. But we can't really do that in the same way because we don't have the same kind of tools. So instead of finding the needle in the haystack, we're going to find the hay in the haystack. Because we know if only there existed one, we could have chosen it generically. So we're going to choose it generically from the get-go in our proof. Now, how do you prove something very generically? So the way that we're going to do it is the thetas are the things that we want to choose generically, right? We want them to be kind of very independent of each other. We don't want to have any dependencies between them. Call them variables for a second and ignore the consequences. Okay, now I'm saying we switch to a field of characteristic 2. That's me being mean. We need it for the proof, but why is that fine? If we're proving it for a field of characteristic 2, why do we get it back for R? Well, same argument as I said a second ago. All we're ever proving is non-degeneracy of some polynomials, some determinants of some matrices. Okay, if they're not going to go to 0 over characteristic 2, they're not going to go to 0 over characteristic 0. Okay. Now, this is just as a reminder. This I wrote before, but just so you remind yourself what it looks like. Right, we have our semigroup algebra here. We pick these elements in degree 1, which is just I put a little variable where these theta here are going to be in the field. Normally, we're going to vary them within it. These are just typo. There should be a p here, an xp. Imagine right here it said x to the p. Sorry. Then it's correct. So it's not just a sum of elements of lambdas, basically, not just a sum of field elements. It's a linear sum, a linear combination of these variables given by the polytope points, the lattice point. Okay, fine. Here's the key lemma. If we have our IDP reflexive lattice polytope, and we take our Artinian reduction, our Chow ring, over a field of characteristic 2. Here you want it to be infinite, just so you have enough room for the thetas. You can ignore it in a second. Then we get this formula for our degrees, where the degree, right, was just this isomorphism. So really, I'm just saying there's many different ways of representing something in here, but it's just isomorphic to the field. And I want to be able to describe what one of these maps to in terms of the elements sort of surrounding it. If you stare at it for a while, you might be able to see why we called it a possible analysis, possible type identity, because it's quite reminiscent of the original one. Again, notice here I didn't put the theta there, but notice this depends on our choice of thetas. And now, if you actually look at it instead as a function in the thetas as variables, it'll be a rational function, I claim. And if we actually have that, if we have our degree function depending on our thetas as a rational function, and we have this beautiful identity here, which is really just a technical consequence at the moment of a balancing analogous to the simplicial case. It's quite mysterious still where it's coming from. And similar things should hold for other characteristics, other finite characteristics. But the formulas become much more ugly, because why do we use characteristic 2 to begin with? We use it for the same reason any lazy mathematician uses it. It's a beautiful even prime, but mostly a lot of things cancel. So in actually proving this, you have to keep canceling things again and again and again and again and again. And eventually, you end up with this quite magical formula. And what we actually use it for is the following: see your degree function as a rational function and differentiate along a phase. Because now, if you literally plug a differential operator into the formula we just had a second ago and specialize not to just any element at the top, but one that comes as a square from something in the middle, plug it in within 2 minutes. Anybody who's bored as an exercise, you'll be able to prove this formula. Now, the reason we care about this is to get the following. We need to strengthen the perfect pairing, right? I said that given a reflexive polytope, we have a pairing at the bottom. Okay, I'm going to put this first. We have a pairing. Ignore the tildes for a second. We have this perfect pairing. So for any element here, I can find an element here such that the multiplication is non-zero. For any element, I can find something that it pairs to. Okay, the pairing is integral to actually proving a Lefschetz theorem generically. But when you're actually proving this, the problem that you keep running into is you have one of these elements, you know it pairs to something, but you need to actually relate it nicely. You need to find something sort of close enough within an ideal that pairs to it. You need to sort of localize everything. Where localize, I mean in the geometric, in the hand wavy picture way, not in the algebra way. And what we actually do here is strengthen this pairing so much. Sort of the most extreme kind of pairing that you could wish for is take something in the middle, pair it with itself. Maybe that works. Now, generally, it's really not going to work. But if we do a little bit of trickery, it does. So what we have to do in order to do that is really keep considering our thetas as variables. and take as the field purely a transcendental field extension over our original field. So we keep them as independent as they possibly could be. And then we get that for any element u in degree half, we can pair it not only with something or something close, we can pair it with itself. And from there, you can prove Lefschetz. Technically, in order to prove it nicely, you need to go to a slightly higher generality of spheres and not just lattice polytopes. And on the way, you prove a proper generalization of the simple spherology theorem, where you recover the other one back by pretending that your lattice polytopes are unimodular. You sort of go reverse. So this is a proper strengthening at the end. But the key that you really use is this amazing idea of Papadakis and Petrotou to really wish for the most extreme pairing that you could possibly have. Now, if you want to very quickly see the rough idea of how to go from this to this, well, okay, for every u in half degree, we want to find something that it pairs. You want to pair it to itself, right? Okay, depending on the thetas, those are variables. Well, take your u. You want that this here is non-zero, right? You want to pair it with itself and hope for the best that this isn't zero. But we know that we have a pairing. So we know that there is something that it pairs to. In particular, you're going to be able to find an xf of this type. So you know that this, for the correct choice of f, for the correct face in the thing, this is not going to be zero. The square is not going to be zero. So this being dependent on theta is not going to be identically zero. So in particular, for some choice of thetas, it's not going to be zero for a generic enough choice. So if we choose them as variables that never interact other than being put into the field as an extension, we really get this pairing to never degenerate. And from that, we get Lefschetz, and from that, we get the unimodality. All right, I'll stop here. Thank you.
Great. Let's thank the speaker for a wonderful talk. Are there questions?
Sure, I had a question. So thanks, Johanna, for a really nice talk. Very pretty result. So now that the Hibi Ohsugi conjecture is proved, one could ask, are there other stronger properties that the H-star sequence has, so such as being gamma positive? Or, I mean, we could even wish for maybe real roots, but that may be too much.
Yeah, I think there's counterexamples for real roots. And
gamma positivity then?
I have no clue, to be perfectly honest. I doubt it. I highly doubt it. I mean, yeah, gamma positivity I simply never thought about, but there's probably a fast reason why it should be false.
Gotcha.
But I might be saying something wrong here. Does anybody know? I mean, there's already the issue with gamma positivity, I just don't know. The classic question that people ask is log concavity for special cases, which isn't exactly something that you would expect, because they don't you get the log concavity more of something and sort of behaves as if it was intersection numbers. And you get this more, you get only the unimodality if it behaves more like the Betty numbers of some variety. Right, you prove something entirely different at the end. For the log concavity, you prove a Hodge-Riemann relations in a larger ring, right?
Right.
and then multiply these things through. So that's just not something I'd expect in count with the degree of natural.
Gotcha. Okay, sounds good.
There's a question in the chat.
Mm-hmm.
Michelle asks whether the sequence, probably that means the H stars, is palindromic.
Yes, I mean you get the palindrome. Oh wait, I put the faces over the presentation, so now I don't really see what slide I'm on. You get the palindrome immediately for anything reflexive, right? So this is the consequence of the perfect pairing. This is effectively the Poincaré pairing of the boundary sphere. I mean, you really have this as a generalization of the symmetrical sphere case, where you get the palindrome for any sphere. So effectively, I mean, really, you have the pairing of the thing with the relative ring instead, right? With the relative object, and then if that given nice enough. And then if the boundary is empty, then you get the perfect pairing. So you get it for the spheres, and you get the same here if you don't just consider lattice polytopes, but you glue lattice polytopes together to form a larger complex, where I don't care where they're embedded. I just care that on the boundaries, the lattice structures agree. Then you get the pairing for those larger objects as well. And so in that generality, you get the palindrome, yes. And in particular for reflexive polytopes. Because looking at for reflexive polytope, looking at its structure is effectively equivalent to looking at the structure of the boundary. That's the whole reason why they're special, because they behave just as the star, just sort of as a star where the boundary is the link. They just behave as a cone over the boundary sphere.